In this video, I'm going to explain how to handle data that has been collected in an open flow experiment with, in this case, 3 channels. And we had, of course, channel 1 was the reference, and in channel 2 and 3, we had frogs. Channel 2 had a smaller frog, and channel 3 had a larger frog. We're looking here at page 1 of the experimental file which displays the raw data of all the parameters that have been measured. In this case, we're looking at CO2 data, oxygen, flow rate, temperature, and atmospheric pressure. And the data is displayed in graphs and in a table. And when the experiment was running, of course, the meters were also showing individual values. These here pink windows are the user parameters that we've discussed before, and I'll go through them again while discussing this data. So when you're looking at the raw data, a few things to note. For CO2 measurements, you will see that there is CO2 measurements for each of the animal chambers and the reference. The reference is always measured at the beginning. We used mode 0, which means that reference was measured at the beginning of each cycle. So reference was channel 1, followed by channel 2 and 3, and then back to reference. The reference measurements are always indicated by these red crosses. I'm going to just expand this graph a little bit so you can see things a bit more clearly. But basically, red cross is when the system switches from the reference or channel 1 to the next channel. So in this case, reference is measured between 0 and the red cross, and the reference is measured again here, and again here, and so on. The red circles represent measurements of subsequent chambers, in this case, chamber 2. This is where chamber 2 switches from, the switch occurs from chamber 2 to the next chamber. So the measurements of chamber 2 are between the red dot and the red cross. And then, because we only had 3 channels here, the last channel in the cycle was channel 3, and the last channel of every cycle is marked by this orange triangle. That's when the switch occurs from the last channel to the next channel, in this case back to channel 1. So the measurements between this orange triangle and this red dot are for channel 3. So the reference being measured only for in channel 1 is interpolated between those measurements. So you can see there's a dark line here representing the reference measurements when it's being interpolated between the channel 1 measurement here and channel 1 measurement there. This is very useful and important because especially if you have drift, like in this case with the oxygen data. I'll stretch this out here. You can see that the reference is drifting down a bit. So it's very important because the data is corrected for that drift when differentials are calculated, and that is done on page 2. I'm just going to go back here to 0 so you can see that more clearly, and you can see that now the reference is brought to 0. It's been subtracted from all the data, and the differentials of CO2 and O2 for each channel are plotted here. So this here is data measured in channel 1, channel 2 I should say. 1 is the reference. This data here is measured in channel 3. I'm just going to go back again to raw data here, just so we can go through some more of the important things that I need to mention. And because we had 2 different size animals here, we have different activities. Of course, the larger animals are going to have a stronger signals, CO2 and O2, than smaller animals. This system, this S159, was set up with a CO2 analyzer for 0 to 2000 parts per million range. So it's important that you do not exceed that range. So when you have a larger animal, you may have to have a higher flow rate to make sure that the signal is on your, within the range of the analyzer. So we actually had different flow rates in channel 1 and 2 versus channel 3, and that was to demonstrate how you can affect the signal that's being measured by changing your flow rate. We wanted to bring both signals close to similar levels, and we achieved that by having higher flow rate in the chamber 3 or channel 3 with a larger animal, more active animal. But in actual experiments, we actually recommend that the animal size is kept similar, so the response time is going to be similar and the response level similar, so you can have the same flow rate. And that's important because the flow rate is going to be affected by dwell time as well. As you remember, in previous previous videos, I've explained that user parameter that has to be set up before the start of the experiment is dwell time, number of channels, and the mode. Number of channels, that's obvious. You're only collecting data for channels that you're using. The mode, I've already mentioned before, is 0 being the most frequently used mode when you're measuring reference at the beginning of each cycle, and mode 1 is the mode that is used when you're measuring reference after each channel. So you measure 1, 2, 1, 3, and back to 1. But this data is collected in mode 0, so I need to go back to that so the data makes sense here. And the dwell time, of course, is important because the dwell time has to be long enough to flush the chamber and be able to get steady state readings of the next channel. And the flow rate and dwell time are very closely linked together. You've got to make sure that your flow rate is high enough to flush the chamber at least 3-4 times during the dwell time that you're using. So we recommend to actually run some trial experiments at the beginning, that for a few cycles to determine the optimal dwell time and the optimal flow rate for your experiment. Okay, so I've already explained the symbols here, so we can move on to page 2. Page 2 is where the differentials are displayed, and this is the page where you can set up the other two parameters, user parameters, event time and O2 delay. Event time is a period of time from the switch. So for example, here when you switch from channel 3 back to channel 1, the event time is a period of time that the software will average the data in the calculations. So that event time should be approximately 1/3 of the dwell time. So in this case, we have dwell time of 3 minutes, event time of 1 minute is sufficient. It basically means that 1 minute of the data from the switch is being averaged in all the calculations, and I've highlighted approximately 1 minute. If you look here, delta x 1, and that's what this data is indicating. The O2 delay is a parameter which aligns the CO2 and O2 signals, and it's important that this parameter is checked because depending on the flow rate that you're using in your experiment, you may find that the CO2 and O2 signals are not completely aligned, and that is the reason for that is because the oxygen analyzer is after the CO2 analyzer. So CO2 is measured first and then oxygen. So at low flow rates, you may find that the signals are not fully aligned. And as you know, as CO2 is produced, oxygen is consumed, so that they mirror each other. And to check for this alignment, we recommend that you zoom in to maybe a cycle or two, and then you can go here and select this examine icon, and you'll get a cursor show up. And we recommend that you go to a point of deflection where it's easy to see whether the signals are aligned. And if they are aligned, like they are here, you can easily see that. But if they are not, then you would have to adjust this O2 delay parameter until they are aligned. I've just misaligned them by increasing that to 2, and you can see that now the CO2 signal is delayed by a couple of points. So I'm going to go back to where it was, because in this case, there's no need to make adjustments to O2 delay. The signal is aligned. So I'll exit out of this examine. So now, with these parameters set up, you can now look at your summary data, which is on page 3. And if all the user parameters have been set correctly, then the summary calculations are going to be correct as well. And the parameters that you see on the summary page are the VCO2, VO2, and the ratio of the two, which is the RQ, the respiratory quotient. Because in this system, the flow monitor is built into the S159, so the flow rate is measured after each chamber or downstream. The formulas that are used are appropriate for downstream flow calculations. If, however, you had an S159 analyzer which didn't have a flow monitor built in, the flow monitor was set up upstream of the animal chambers, there would be different calculations set up in the experimental file. So that's something important to point out. So the VO2, VCO2 data is shown, as individual points. Remember that for each dwell time, there is a single average point calculated over the event time. And then you also have the data showing and displayed in this table for each of the dwell periods. And I just passed here the VCO2, VO2 for channel 2, and for channel 3, if you keep scrolling down, you'll get to see the data from channel 3 as well. And each of these points is going to be in the table here. Now, to get this data exported or copied, there are two options. One is that you can, actually physically go and highlight your data, okay, like this, copy, and then go into Excel spreadsheet and paste it. You have to put in your titles, because the titles don't copy. So VCO2 channel 2, and the data is going to be, of course, down somewhere appropriate to the time period that it was measured. So that's one way you can do it, and you'll have to manipulate your Excel spreadsheet file to delete the empty columns, which right now I've got here, delete, to get rid of it and make a sort of a small summary table. So that's one way of doing it. Another way of doing it is to go into File and Export As, select CSV, and then save your data. I've already had it saved, so I'm just saving over it. And then you can go back and open the exported file data to show, in the spreadsheet like this, convert, and to show all the data. All the raw data is going to be exported, of course. All of the control parameters that are used to control the system are going to be exported, and the actual summary data is going to be at the end in these last columns, just like they were in the Logger Pro file. And again, it's going to take some cleanup and deletion of empty rows, to get a sort of small compact summary table. But that's another way of getting the data out from Logger Pro. So in summary, this is how you would handle your OpenFlow data. One more thing to mention is that, and I mentioned that in previous videos, Logger Pro does not automatically save the data when you're collecting it. It's really, really important that during data collection, periodically you come here to Go File, Save As, and save your experimental data under the name that you've selected, or give it a new name if you're saving it for different time periods. So that's important, is to set up this periodic saving of data so you don't lose anything. And remember that the data that you do get in your summary tables and summary graphs is the average values that have been calculated for each of the dwell times. So you see that in here we used 3 channels. Channel 4 will have no data. Okay, that's all that I'm going to say about OpenFlow. Thank you.